So we've got recording, we've got things going here. So we're going to look at the work associated with a chin-up. And so we've got our person hanging off here. And again, we all know that I am not the best artiste. And we know that the bicep can impart a force of 800 newtons. And the distance that the bicep is going to move through this, doing this force, so our change in distance is going to be 7.5 centimeters, and our person is going to have a mass of 75 kilograms. And we want to know the work of the muscle. We want to know the work of the muscle. So it's going to be pretty straightforward. The work of the muscle is going to be 800 newtons. I have to convert centimeters to meters, and that's going to give me 60 joules. I just multiply 0.075 times 800. But this is the work for one muscle. So if I'm doing one hand pull-ups, that would be the work done. But I don't usually do one hand pull-ups. Well, I don't usually do pull-ups. Let's just be honest. Pull-ups and chin-ups and pull-ups were never my thing. Ever. Ever, ever. So if I was having to pass my physical test to get into one of the academies, this was my problem. So we want to look at it for two muscles. We get some multiplied by 2, and the total work done is going to be 120 newtons. But let's look at the work done. Huh? Oh, Jules.
Okay, I was like...
Thanks. You're right. It's early in the morning, and if it weren't for the fact that I set 2 alarms this morning, I would have had trouble. That's 120 joules. So, but the average person, when they're doing a chin-up, they're really moving 40 centimeters. Okay? They're really moving 40 centimeters. So the total work done when you're doing a chin-up is going to be my change in energy, right? And it's going to be my change in potential energy, which is going to be mgh, which is going to be the mass that I'm lifting, times gravity, times the height. So if I'm lifting a person that is 75 kilograms, 9.8, and I'm doing 0.4, that's going to be kilograms, meters per second squared, meters, which gives me my joules. It's going to tell me it's 294 joules. So 294 joules worth of work had to be done in order to lift the person. It's obvious that the bicep was not doing it by itself. We have other muscles involved in order to do that. We have other muscles involved in order to do that. Because there's no way my little bicep is going to be able to do it by itself. So for those of you athletic trainer types, for those of you working in physiology and anatomy, you know, this is one of those things you have to start thinking about what other muscles might be involved. And if anybody has pulled muscles in the chest, you know your chest muscles are involved. because it's not going to be easy, and you know you have upper back muscles that are in there. And then you got your trapezius and all those other ones. All right, we're going to do this one next, and then we'll do some power ones. If you've ever looked under the car, some cars have what are known as leaf springs. Okay? They have leaf springs underneath that look like that. Some will have leaf springs with a coil spring in there as well for shock absorbers. Another type of leaf spring, if I've looked at an old buggy, you'll see springs that look like this on an old buggy. We're going to have a spring that looks like that. The thing about these springs is you have one or more spring in there, and usually what happens is you have what they call the main spring. In this case, we're going to say the leaf spring. And it's going to have an equivalent K of 5.25 times 10 to the 5th Newton meters. And remember, my spring is based on its material. And for you biology types, I even think there's a homework problem. Is there a grasshopper homework problem? I have assigned a grasshopper homework problem multiple times where the grasshopper is leaping off the ground. A grasshopper's leg and a frog's leg actually work like springs. And Hook, our good old guy from Hook's Law, that's what he was looking at. Hook was kind of an interesting dude. He got into a lot of fights. He was always arguing with people. But he actually, not only does he draw a flea, he actually was looking at fleas and frogs and everything else, looking at springs, which is why we have Hook's Law. But he was really a biologist. He also he's also the one that actually got that frog's legs twitch due to electricity. So Hook is kind of an interesting guy. But this is, so we can look at muscles as springs. And I have a helper spring, which is going to be 3.60 times 10 to the 5th Newton meters for my spring constant.
So is that a K, or what do you?
Yes, it's a K. It's the small letter K.
Okay, I wasn't sure.
It's a script K.
Okay, I wasn't sure.
Those are my spring constants. And it comes from F is equal to minus KX, or my potential energy for a spring, which we're going to need here in just a second, is 1/2 KX squared. And remember, this negative sign comes from the fact that the spring is usually giving us a restorative force. So if I'm worried about direction for my force, I have to take that into account. But most of the time, we're looking at the magnitude of the force associated with the spring, because my spring is going to oscillate. But the negative comes from the fact that it's a restoring force. Now, when we do a leaf spring, what happens with a leaf and a helper spring is one is going to be the primary spring, and then after a certain amount of compression, the helper spring is going to kick in. So the helper spring is going to kick in, and so we're going to use y is equal to 0 for when the helper spring kicks in. So when I compress the spring until it reaches y equals 0, I'm only going to get the leaf spring involved. So I'm going to look at forces here. I'm going to have the force of the spring associated with the leaf spring, that's what the L is going to be, plus the force of the spring, of the helper spring, is going to kick in for the weight of the load. And we're told what we want to do, here's the question, is if the load is 5 times 10 to the 5th newtons, we're going to have my leaf spring, or my helper spring kicks in at 0.5 meters. We want to know what is the compression of the leaf spring. And then we want to know the work done. And we got to know this so we can do the work, because the work is going to be 1/2 kx squared. And the total work is going to be 1/2 k of the leaf spring, its compression, plus 1/2 k h squared. So I've got to know what's the compression in order to do the calculation.
Is that K?
One is for the helper spring, one is for the leaf spring. Subscripts really, really help you keep track of what it is you're working with. So if I start up here, back to this, I've got the force of the spring with the leaf plus the force of the spring with the helper is going to give me the weight load. So F of my leaf spring is going to be minus the K associated with the leaf spring times its compression. And we're going to use Y because the problem gave us Y naught. The helper spring kicks in when Y is minus Y naught. So the helper spring doesn't kick in until I've gone through a certain distance. And this gives me the weight of the load. I'm solving for Y. So I'm going to get, and this is going to be KH. So I'm going to get minus KLY minus KHY plus KHY naught is equal to the weight. Y is minus KL minus KH is equal to the weight minus KH Y naught. So Y ends up being the weight minus KH Y naught divided by minus KL plus KH. Plug in numbers. This is 3.60 times 10 to the 5th plus 5.25 times 10 to the 5th. And this is Newton meters. Meters cancel here. I get newtons over newtons. Newtons will cancel. I get 1 over meters, so I've done everything right, and I end up with meters. And I end up with a negative 0.768 meters. I just take that number, plug it back into here, and I'll end up with the work being done as 1.68 times 10 to the 5th joules.
Can you move the copies?
You want it down?
No, she's over. Okay.
Which part do you need?
That one.
Okay.
Is that 8 or 5?
An 8. This is an 8, and that's a 5.
10 to the 6th?
No, it's 10 to the 5th. Good? Okay. Remember, I think we've talked about it, power is defined as work per unit time. It's going to give us joules per second, which gives us watts. So if I have a crane that's raising 1,000 kilogram weight, and we have a 500 watt crane, we want to know how long okay, I've got 1,000 kilogram weight. My crane is only 500 watts. We want to know how long it takes to lift the object 5 meters from the dock to the deck of the ship. We actually did this calculation, several of us did at the ACS meeting because we were right outside the Dole loading dock in San Diego. And we were all calculating what was the wattage of the crane because we knew, because the containers were labeled with their gross weight, and we were watching how fast these cranes could lift these things onto the ship deck. So you knew what the turnaround time was on the ship. And I had somebody actually calculate how many bananas would be on the plane, because one of the containers actually stated how many bananas was typically in a container. Didn't have one for pineapples. It did have one for bananas. So, you go to a conference like that, they're a little geeky. So power is going to equal the work, which is going to be mgh, because that's my change in potential energy, divided by the time. I want to solve for time. Time is going to be mgh divided by power. So I'm going to have 1,000 kilograms times 9.8 times 5, and this is in meters per second squared. This is in meters. Divided by my 500 watts, which is a joule second. Kilogram meters squared seconds, or kilogram meters is meters squared, meters per squared second squared, that's a joule. Joules are up there. Time ends up in seconds, which is exactly what I want. And when I multiply that in there, I end up with 98 seconds. And if I want to convert that into minutes, it's 1.6 minutes.
So you divide by 60.
Yep. Questions? Okay. All right, light bulbs used to be measured in watts. Incandescent light bulbs were measured in watts because that's how we rated them. That is not watts, and their brightness are not the same. Brightness is measured in lumen. Okay, brightness is measured in lumen. So we want to know how much energy is required by a 60-watt light bulb. This is the old incandescent style. Over its life. And the life of an incandescent bulb is about 500 hours. Unless you have dogs or cats. Because if I could get 500 hours out of an incandescent light bulb, I was doing great. That's one of the nice features of an LED. Cat can knock the lamp off the table and it's not going to kill my LED. Cat knocks the lamp off the table, my incandescent light bulb is toast. Because it breaks the filament. Alright, so power is equal to work divided by time. So power times time is going to equal the work. That is an energy. Okay, so we're going to take our 60 watts times our 500 hours. It's going to give us a lovely unit that we're all familiar with. It's called a watt hour. Turns out a watt hour is equivalent to, you can convert it over, that works. But a watt hour, if I do that, I get 30,000 watt hours. But if I look at my electric bill measures it in kilowatt hours. And that gives me 30 kilowatt hours. Typical cost for electricity is 10 cents per kilowatt hour. Which means the cost to operate over its life is going to be $3. So we're going to do an analysis. Okay, we're going to do an analysis. So if I do a compact fluorescent light bulb to give you the equivalent lumens of a 60-watt bulb. Okay?
That's longer, I'm sure.
Well, we're about to do that. We're about to do it. Compact fluorescence to give me the equivalent lumens takes about 10 watts to operate. And it's going to last about 10,000 hours. An LED takes about 5 watts to operate, and it's going to last 50,000 hours, roughly. Okay. So if I'm doing this, so if I do my compact fluorescent, so my compact fluorescent, the energy that's going to be required is 10 times my 10,000 hours. I didn't bring my handy dandy note. I've done this calculation several times. It's 100,000 watt hours, but I'm going to go ahead and put it in kilowatt hours just to keep it easier. It's going to be 100 kilowatt hours. And if I use my 10 cents, right? It's going to cost me about $10 to operate for its entire life. Okay, so it takes me $3 to operate an incandescent light bulb for 500 hours. If I take my 10,000 hours divided by my 500 hours, that tells me I need 20 incandescents for every one compact fluorescent. Okay, so that's going to be, so for the same amount of time, my incandescent is going to cost me, it's going to cost me $60 to operate. Now let's do the LED. I mean, 250,000 watt hours. Gives me 250 kilowatt hours, which cost me $25 to operate. Equivalent incandescent going to take me 100 of them. So it's going to cost me $300 to operate incandescents compared to my LEDs. If I do my compact fluorescents, it's going to take me 5 of them. It's going to take me $50 on my compact fluorescents.
Why is it saying money?
My LEDs are the cheapest to operate over time. My compact fluorescents are next, and my incandescents are a pain in the tushy. So now I'm going to ask you why people resisted changing over to LEDs until they had to.
Because they're more expensive to buy.
Their initial upfront cost was more expensive. That was the first thing. But then they got down to, you buy an LED, for, they're getting pretty comparable now. You can buy a pack of them for, $10, a pack of 4 for $10. So the costs have now come down considerably, and that's one of the things. But there was another reason, even having done this calculation over and over and over and over and over and over and over again, I was a late adopter to LEDs. Anybody have any idea why?
Politics.
Nope, wasn't even politics.
How they work.
Wasn't even how they worked. Well, in one case, that's kind of how it is. It's sort of how it worked. But why do people, first of all, why do people do not like compact fluorescents in the bathroom?
False light.
Right.
It's not a very good one. It's not natural light.
It makes you look green and yellow, right? makes you look sour and sick. And that's actually what the compact fluorescents, first of all, they also have mercury in them because they're a mercury vapor lamp. It's a plasma. And so the white light actually has a bluish tinge to it, and with human skin, it will discolor your skin a little bit because of how light interacts with your skin. So it's going to give you a false color. So a lot of people don't like compact fluorescents, one, for the false color that you're going to get. The other reason they don't like compact fluorescents is the old ones, you know, and we all know when a compact fluorescent's about to go, right? Because what happens to it?
Just click.
It flickers. So if you have a high sensitivity to the rapid flickering rate, which is 60 hertz, a lot of people don't like the compact fluorescents just because of the flicker. And even like in these rooms, well, these rooms are now, a lot of these rooms that we're in have more the LED type, even though they look like this room actually is compact fluorescent. These are fluorescent ones in here in Tonkawa. But in other places, you'll get the LED type and you won't get that flicker. So that's one thing that people didn't switch, because I hated compact fluorescents from that reason. The other is decorative, because a compact fluorescent is going to be a little screw kind of thing, and it's going to be harder to put in your lamps. And so people didn't switch to compact fluorescents for a variety of reasons, and that's one of them. And it's not until recently that the LED could actually give you the mixture of wavelengths and light that your eye was comfortable with. The human eye needs a little bit more of the blue, and that's why they talk about blue light and a few other things right now. So the LED, for those of us who were late adopters of LEDs, is because the light was not, it actually tired you a lot more because of how your eye worked with the light that was generated from an LED. A lot of that's been corrected now over time, so your LEDs give you a much better spectrum of light, and so that's one reason that LEDs were late adopters. The other is my compact fluorescents, or my regular incandescent light would give you illumination like this, and we all know about LEDs, it's almost a direct light. And that's why I hate LED headlights, because there's no diffusion out of the LED headlights, and they are just painful. And so it took LEDs a while to be able to give you more of that dispersive light as well. So that's why LEDs, even though it is super, incredibly cheaper to operate, and you're not replacing them all the time, which is also nice. You put one LED in and you can expect, for the most part, not all LEDs work that way, but for the most part, you can expect a relatively long life on your LED. You've got a lot of difference, which is also what's nice about Christmas lights, because now you can put huge strings of LED Christmas lights up, and you're not draining your electric bill as much when you're dealing with it. So that's one of the kind of the interesting thing to look at energy and power, and why LEDs are good, and why we have a different energy. Which is now the politics are, if you want to save energy for your grid, change out your LED or change out your incandescents, because your incandescents are really what's going to drain electricity and raise your electric bill. So I always like to do that one. So let's do a little bit more of a complicated problem. We've got an electric motor. And this is of a model train. Accelerates the train from rest to 0.62 meters per second in 21 milliseconds. Oops. Milliseconds. It has a mass of 875 grams. We want to find the average power. We want to find the average power. So power is work divided by time. Work is going to be force times my distance, but that's going to be mass times my acceleration times my distance. I've been given mass. I've not been given acceleration, and I've not been given distance. So I've got to use my kinematics to figure that out. So velocity is going to equal my initial velocity plus my acceleration times time. We do have our final velocity. We know that that velocity is 0, so I can use this information to find acceleration. So I'm going to get my acceleration is going to be my velocity divided by time. It's going to be my 0.62 meters per second divided by my 21 times 10 to the minus 3 seconds. Gives you 29.5 meters per second squared. My change in distance is equal to my initial velocity times time plus 1/2 AT squared. You know that goes to 0. So this gives me 1/2 29.5 meters per second squared times my 21 times 10 to the minus 3 seconds, and all that has to be squared. Gives me a distance of 0.0065 meters. So my work is going to be my 875, which has got to be changed over to kilograms, so divide by 1,000 kilograms times my 29.5 times my 0.0065 divided by the time, which is 21 times 10 to the minus 3 seconds, and that gives me about 8 watts. Questions? Okie dokie. All right. Love inclined planes, right? Physicists love inclined planes. This time I have a spring at the bottom. I've got a mass. So we're thinking pinball here. The spring has a spring constant of 36 Newton meters. My ball has a mass of 8 grams. We're told this incline is 30 degrees. We're going to neglect friction for this problem. We're going to add friction in the next problem. But right now we're going to neglect friction. We want to know how high the ball goes up the plane. Given, let's see, given that we compress the spring 4.2 centimeters. So the distance that we're gonna find is distance traveled. So the first thing I'm going to do is I'm going to calculate the potential energy of the spring. It's 1/2 36 Newton meters. Distance, and I'm going to have to convert. That's 0.042 meters squared. Gives me Newton meters. Gives me my potential energy of 0.3175 joules. Conservation of energy says if I neglect friction, that the energy at the top has to equal the potential energy of the spring. And we know the energy at the top is now the potential energy of the ball. And that, if I'm using my system here, is going to give me how high it goes up. So that's going to be mgh is equal to the potential energy of the spring. But I don't want h, I want d. Well, h is equal to d sine theta. Because there's my incline, there's my hypotenuse, there's my d sine theta. So now I can plug this in and I can get mgh, which is mgd sine theta is equal to the potential energy of the spring. D, which is what I'm after, is going to be the potential energy of the spring divided by mg sine theta, which is going to be 0.03175 divided by 0.008 kilograms, 9.8 meters per second squared, sine of 30 degrees. D ends up being 0.81 meters. Guys good? Questions? All right, we're going to tie everything together. We're going to do a cool problem. And then we'll call it quits for today. All right. So I got a spring on this end. The spring is going to have a spring constant of 160 Newton meters. This surface, we can neglect friction. This surface, we can't neglect friction. And it's gonna be a 2-meter long section. It's gonna have a coefficient of friction for kinetic friction of 0.3. We're gonna take an object up here that has a mass of 10 kilograms, and it's 0.8 meters above this surface. We want to know the compression of the spring. Okay? We want to know the compression of the spring. Well, for this part, we can neglect friction. This part, we can't neglect friction. So we have conservative and non-conservative energy in the system. So there's some things I'm going to have to know. One is when this ball gets over this pot, I'm going to need the force due to friction. So let's look at the force due to friction. Force due to friction is going to equal the coefficient of kinetic friction times the normal force. I got to know the normal force, and that's going to be the mass times gravity. So I can calculate my force due to friction, which is going to be 0.3, 10 kilograms, 9.8 meters per second squared, and I can calculate that, and my force due to friction is 29.4 newtons. Now, we're going to take this part first. We're going to look at the work done by friction. Okay, the work done by friction. Remember, work is going to equal force times my change in distance. So in this case, the work done by friction is going to be my force due to friction times the distance. So I'm going to end up with my 2.4 times 2, or 29.4 times 2 is going to be 58.8 joules. And that's the work that's done by friction. Okay, so let's start with the total energy in the system. Total energy in the system is just going to equal the potential energy at the top, which is 10 times 9.8 times my 0.8, which gives me 78.4 joules. So when I come down here, the kinetic energy at this point is equal to 78.4 joules. Because as I've come down the curve, I haven't lost any energy because this is, I can neglect friction here, and I know I'm at this spot. Well, now if I go over the rough spot, I lose energy, right? Because I've lost it due to heat, due to friction. So the energy at this spot is going to equal the total energy of the system minus the work done by friction. So that's gonna be 78.4 joules minus 58.8 joules is equal to 19.6 joules. That's all the energy that I have left to compress the spring. So the energy to compress the spring, that's the potential energy of the compressed spring, is now going to equal 19.6 joules. That equals 1/2 kx squared. So I'm going to get 2 times 19.6 joules divided by k is going to equal x squared. I get 2 19.6. We're going to do the unit analysis here in just a second. 160. So I got joules divided by Newton meters. My joule is a Newton meter divided by Newton meters. Newtons cancel. I end up with meters squared. That's a good thing because I'm in x here. And if I do this, x squared equals 0.245 meters squared. Take the square root, and I get x is equal to about 0.5 meters. We'll do one more. I got a good one. Another practical type problem. We've all seen them. We have these devices. So we're going to look from upper. So this is my concrete slab. Okay, this is the pillar for my bridge. And we've got these things that are there so that if my car hits it, right, it's going to collapse and I'm going to end up dealing with a variety of things. So if I start out with a 5,000 kilogram car traveling at 27 meters per second, which is about 60 miles an hour, and in this case, we're going to have it fall in, okay? We're going to have it fall in. We're going to do it as, because those things I'm seeing them in my head, probably about 5 meters, right? And that would probably be about right, 5 meters or 15 feet. So we'll say it compresses 5 meters. We want to calculate the work done by our restraining device. Okay? So we know the potential energy, or we know the kinetic energy going in. So the kinetic energy going in is going to equal 1/2 mv squared, which is going to be 1/2 5,000 kilograms times my 27 meters per second squared. gonna give me 1.83 times 10 to the 6th joules. That's gonna equal the work done by my object, because that's how much energy is end up being taken in by that object. So if I do that, I want to calculate the force. So now I want to calculate force. So the force is going to be that number divided by the distance. And our distance is 5 meters. We end up with a force that's applied of 3.65 times 10 to the 5th newtons. I want to compare that to the force that we get with our lovely concrete. And in that case, the distance that we're going to have is probably 1 meter, the hood of our car. Compared to 1.83 times 10 to the 6th newtons. Because I'm divided by 1 meter. These lovelies help us out tremendously and makes the crash survivable. Makes the crash survivable. And when we start with impact and momentum, we'll see that more. All right. See you on Friday.